record on this computer. Hello, any questions so far about the So any questions so far? Let me quickly review what we talked about over this semester. So we talked about how we write the programming properly and how do you make sure your algorithm is correct. In lecture 1 and lecture 2, we talked about asymptotic notation. Why we use asymptotic notation? Because the precise analysis is very tough. Rather than doing this, then when it is a small value, it is hard to expect it, but when the values are big enough, I can estimate your program is slower than this and faster than this, and I can guarantee that. That is asymptotic notation. We are using this because we don't know precisely, but we can estimate roughly, okay? Then from there, we talked about the worst case complexity, and we don't really care about the best case, we don't really care about the average case, but we care about the worst case. Then we learned the big O notation, big omega, and big zeta. In lecture 3, we analyzed the program side by side. And we did some examples like this. And we talked about, by example, selection sort and how can we have a zeta of n squared. Then we talked about, in the end, the smaller value, that's not what we care. We care about the ultimate value, and in the end, when the value is big enough. And we care about dominance. When we talk about log n, that is the best one, okay? And when it is the n log n, we can still accept it, but it starts to be n squared and 2 to the power n factorial. We cannot bear this program, okay? And we talked about logarithm. What is logarithm? Logarithm is about doubling it and halving it. So why is the doubling it and halving it is important? Then we can eliminate half of the problem. We can eliminate the half of the problem. Then we can make more smaller and smaller pieces. Then we can conquer, which means we can rule the example more efficiently. So, and we talked about, in lecture 4, we talked about the elementary data structures, and we talked about arrays and linked list and how they are efficiently, how can you do this? Mean, the search and insertion and deletion and minimum and maximum find and successor and predecessor. How long does it take? We analyze it step by step, and why is it big O n and why is it big O on? Big O 1, okay? Then we talked about this in all arrays. Today, we're gonna talk about the dictionary. Okay, let's start the class. So one of the students are struggling to joining the lab.
Oh, Professor, you said we're gonna have a quiz at the end of the lecture, right?
No, not the end, in the middle of the class.
Oh, in the middle, oh, okay.
Okay, so dictionary. So what is dictionary? So perhaps the most important class of the data structure, maintain a set of items, so indexed by a key. So let's looking for a value X. How can I get it? So in a search, I'm looking for K, which is my key. So key of X is K. Then I'm looking for this key in the set. Then we can find the value precisely. Then we talked about what is insertion, what is a delete, and we know what it is, right? This is what we talked about. Okay, one second. The student name Kwangmin Kim is keep sending me a message. Trouble to joining. Okay, okay, never mind then. So we know what's the mean and max, how we find the mean and max in array, and the linked list. So I assume everybody knows what is array. I assume everybody knows what is linked list. I can assume everybody knows about what is doubly linked list. Right? Everybody clear about this? Okay. Then problem day, let's solve this problem. So what is the asymptotic notation? Asymptotic worst case running time for each of the 7 fundamental dictionary operations when the data structure is implemented as singly linked list, double linked list, singly linked list, double linked list, when it is unsorted, when it is sorted. Clear? You understand the problem, right? So something like this, we're gonna, what's the time for the singly unsorted search? Anybody?
It's ON because
Right.
it has to go through a linear
Yeah,
search.
right. What is a doubly unsorted?
It's ON.
Still on.
ON
And what
as
is
well.
a sorted?
It's ON.
They're all ON because
ON.
go to linear search.
Doubly sorted.
ON.
ON.
So can you fill out the rest of the values?
Okay.
Okay. Let's do this as a quiz. I have 2 quizzes today. Okay. Quiz 1, long test. Okay. Simple action solution bank. Simply recipient. Why does it need a recipient? Assignment quiz 1, blank, grade importing. Okay, no due date. But the quizzes assign. Quiz. Okay, I just assigned the quiz 1. Let's do this for 5 minutes, maybe 7 minutes.
Professor, where do we write down the answers?
Yeah, and sequentially you can write down. Why does it request the view? Okay, I updated permission, then I'm sure everybody, I think everybody can access to it. You can stop sending me email. Okay, now I'm sure everybody can see the file, right? Okay, let's spend 7 minutes and we're gonna come back at 3:50. Okay, try to submit before 3:50. So Kwangmin,
Yes.
do you understand what this quiz is?
I just got in. So
So
the
fill out
internet
the
connection was
blank.
bad.
So we have a solution bank in here. We understand why is the big O n takes, right? So write your answer. So every blank points in here.
I don't know how to use it.
What do you mean you don't know how to use it?
The user interface is very confusing. Like I don't know which question. Do we just
Oh,
can we just write in the power?
Professor, it's in Korean. How can I change the language?
Really? I never.
Yes.
1 second. So let's do this in this way. So I'm gonna make a new quiz, which is just taking picture of it and upload your pictures. It should be more too simple.
Thank you.
Okay, assignment.
So you mean that we can write down our answers and upload it in the Google Classroom, right?
Yeah, you can take a picture of it,
Okay.
picture of what you wrote, and upload it
Yes.
on the Google Classroom.
All right. Thank you.
All right, so I just made the assignment number 1. So I'm gonna delete the, don't delete it. So I just made a new assignment, quiz 1, same title. So you can take a picture of what you wrote and upload it as a pictures. So Kwangmin, do you understand what we are doing in here?
Yes, I got it. Thank you.
Okay. So Hyungtaek
You
1
just
says,
explain.
is the quiz going to be graded? I'll think about it. Okay, maybe I can use as attendance. So don't worry about it. Don't do an internet search. Try to use your brain. Okay, I will accept the crazy idea. Wrong answer is fine. Okay, don't try to copy from somewhere, but please try to use what you know about it. Okay, then I can have some feedback. Okay, Hyungtaek, say again, please.
Do we have to write reasons for each of the answer?
Not necessary. No, then it is too complex. Okay, so don't worry about your correctness and use this one as tease your time, tease your brain. Okay, if you finished, you can upload first. So 5 turned in. And still waiting for 23. Six of you turned in. 7 of you. Let's wait for a couple of more minutes, then everybody can submit. Let's wait for 5 more minutes. Okay, so 1, 2, 3, 4, 5, 6. 6 of us is still missing. 정민, you, 유정민, PK, Ulbeck, 서영. So you want me to? Okay.
You have submitted to first quiz 1 or second?
Huh? What do you mean?
There are 2 assignments, quiz 1.
Yeah.
You
The
have
later
submitted
one, please. The
later
later
one.
one. Yeah.
Oh. Okay, sorry.
No problem. Let's wait for 2 more minutes. So I think almost everybody submitted. Can I ask you, Jungmin, you submitted? Okay, check it. Maybe Jungmin has a 2 ID.
I submitted.
Okay. Did you? I cannot see your submission. So can you submit on the later one, not the first one? So we have 2 quizzes. One is you can submit on the pictures. So 3 of you turned in the, okay, oh, here you go. Okay, don't worry. So Ulbeck, Roshan, Paudel, Jungmin, all of you, 3 of you in here. Okay, don't worry about it. So, okay, everybody is submitted. Okay, thank you. So, who wants to do insertion? Let's pick the 1, 2, 3, 4, 5, 6 of you and talk about reasoning. Okay, so let me check the attendance sheet. Okay, so I'm gonna check Yuha, hey Yuha, as an insertion. And I'm going to ask Ko So-young as a deletion. Okay, Songjun as a successor. And Hanmin as a predecessor. And Ayong as a minimum.
캠퍼스 거주자분들께서는 다음과
박우현
같은
as a
사항을
maximum.
주의하시어 피해가 없으시기를
Okay,
바랍니다.
ready?
각
Let's
사무실
wait
창문
for
및
1 minute.
복도 창문은
Sorry.
태풍의 날아갈 우려가 있으니 모두 시건하여 주시기 바랍니다. 바람에 날아갈 물건이 주변에 있다면 미리 제거하거나 방제실 및 캠퍼스 근무자에게 신고하여 주시기 바랍니다. 마지막으로 인명사고의 우려가 있사오니 외부 활동을 자제하여 주시기 바랍니다. 감사합니다.
May I have your attention, please? This is Incheon Global Campus Emergency Office. As the 10 typhoon Haishan is heading towards Korea, we need your cooperation to prevent damaging the campus. Please close all windows in the building and put away things that may blow away in the wind. If you find any issues that should be taken care of before the arrival of typhoon, please report to IGC Emergency Office. In addition, please minimize outdoor activities for your safety. Thank you.
인천 글로벌 캠퍼스 통합방제실에서 안내 말씀드립니다. 제10호 태풍 하이선이 우리나라를 향하고 있어 태풍 피해 우려가 있습니다. 캠퍼스 거주자분들께서는 다음과 같은 사항을 주의하시어 피해가 없으시기를 바랍니다. 각 사무실 창문 및 복도 창문은 태풍에 날아갈 우려가 있으니 모두 시건하여 주시기 바랍니다. 바람에 날아갈 물건이 주변에 있다면 미리 제거하거나 방제실 및 캠퍼스 근무자에게 신고하여 주시기 바랍니다. 마지막으로 인명사고의 우려가 있사오니 외부 활동을 자제하여 주시기 바랍니다. 감사합니다.
Okay, let's start from insertion.
Emergency Office. As the 10 typhoon Haishan is heading towards Korea, we need your cooperation to prevent damaging the campus. Please close all windows in the building and put away things that may blow away in the wind. If you find any issues that should be taken care of before the arrival of typhoon, please report to IGC Emergency Office. In addition, please minimize outdoor activities for your safety. Thank you.
Okay, ready? Yuha, insertion.
Insertions, singly unsorted is 01.
Okay, why?
Because it doesn't matter which position we just add it to, so
Okay.
just insert it.
Right, okay,
The
doubly.
doubly is the same 01, and the reason is just the same as well as the
Okay.
singly unsorted. And the singly sorted is ON, because we have to go through the dictionary and find the position to insert.
Okay.
So it takes ON. And then the doubly sorted is the same ON. And this one too, we have to go through the dictionary and find the position we need to insert. So.
Okay, good point. Let's say we know the exact position. Do we still need a big ol' N time in a singly linked list? Let's say I know where exactly I can put it. Do we still need to big ol' N or big ol' 1?
I think it's ON because don't we have to like start from, for example, like the singly sorted, the first one, and then we have to like traverse to the end.
I missed it because of the phone call was just came in. Can you say that again, please?
So I think because it's like linked, we have to start from the starting position and just like find the next link. So I think it's ON still, even if we know.
So you are correct because we have to know this point, right? Therefore, we have to maintain. Is that correct? Perfect. Thank you, Yuha.
Professor, I think the screen is out.
Screen is out. Okay. How about now?
Yep, good. It's back.
Okay, thank you. So, Yuha, thank you. And next one, deletion.
For singly unsorted, I think it's 1.
1, okay.
And then doubly unsorted, it's 1 too. And So singly sorted is ON,
Mm.
and doubly sorted is ON.
And start with the deletion. Why is it O1?
Because it doesn't have to like search through before, so it's O1.
Okay, good point. So, but the truth is, so how does deletion? Deletion works like this. So we can delete this, right? So we have to know this point to delete this guy. So we have to maintain the who's my previous. Therefore, it should be big O N. Okay, big O doubly unsorted because I know who's my previous and I know who's my next. Therefore, I can tell them, okay, go ahead and go ahead. Then therefore, big O1 is correct. Okay, singly sorted.
Sorry, isn't it
Big
O1?
Yeah, big O N is correct because you
it,
have to maintain previous one.
Yeah.
Then sort it back. And doubly sorted is big O1. Why? The same reason. Even if sorted, I have to, even if sorted, deletion is just way, so therefore I have to know. When it's the doubly sorted, I maintain who's my previous and I maintain who's my next. Therefore, I can tell them do this. Therefore, it's big O1.
Okay.
Clear?
Yeah.
Okay, thank you. Good point. It's So Young, right?
Yes.
Thank you. And the successor?
I'm Sungjun, and I think they're all O1.
Successor, big O1. Yeah. Why?
Since linked lists all have, nodes all have the successor, so that's why.
So successor meaning who's after me. So successor in the number is 1, 3, 5, 6, 2, 7. In 3, I have to, let's say from 4. Successor of 4 is not 1. Successor of 4 is a 5.
Oh, really?
Okay. The successor is not linked list. So when it's unsorted, successor of 4 is a 5. So therefore, successor should be, you have to run through.
ON.
ON, okay, correct. Doubly unsorted, ON.
ON as well, yeah.
Okay, when it is sorted, oh, you know exactly what it is. But even if it is sorted, this is not correct because, same reason. Who's my successor? Who's my, meaning, who's the next of me, right?
Okay, so you mean the successor is the next number of the current node, right?
Yeah.
Okay.
Then I can find out in one time. In double links, I can find it one time. Okay, thank you, Sungjun. Okay, who wanted the predecessor?
Hamin, that's me. Yes, so singly unsorted is going to be ON, and doubly unsorted ON, and singly sorted ON, and doubly sorted is going to be O1.
Okay, correct. Okay, so predecessor, yeah.
Yes, so, okay.
Go ahead, I'm sorry.
Okay, for singly unsorted, you have to go through the whole list to find the predecessor. And same for the doubly unsorted. Okay, and for singly sorted, it's gonna be ON.
Yeah.
Because we need to find, yes, it's not linked to it. And for doubly sorted, it's linked to it, so it's gonna be O1.
Okay. All right. So what's the minimum? Who's next? Ion?
I'm Ion, and singly unsorted is ON. Doubly unsorted is same, ON. Singly sorted is O1 and O1.
Okay, correct. So we know what minimum, because it is unsorted, I have to find it. the minimum. When it is sorted, oh, I can find it instantly. Okay, so who's next? Maximum?
I'm Woohyun Park.
Woohyun.
Yeah. I think it's the same for minimum. Singly unsorted would be ON.
Okay.
Doubly unsorted would be ON2.
Okay.
And then singly sorted O1, because it's just the first or last element. Yeah.
All right, perfect. So now I assume everybody understand why is the big O N, big O1, and reasoning behind it. Okay. So this is correct answer. And you're going to see this slide. And let's talk about this one too. We talked about this. So array unsorted and array sorted. Let's fill out this form and let's make a time attack, only 5 minutes, and I'm going to close it as quickly as possible. So fill out this blank spot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to make a quiz 1-1 assignment 1-1. Okay, let's submit your answer as the same thing you did. Okay, just for 5 minutes. Okay, I just received the email. Then I have quizzes. Okay, you start to submit it. Okay, most of you submitted. Yeah, I think almost everybody submitted. Let's quickly review this. Okay, so now it is array. When it is unsorted, search, I have to end time. When it is sorted, I can quickly do binary search, therefore log n. Insertion, I can do it instantly. If it is sorted, I have to find the right form, right spot, then I have to push everybody. That takes n time. When it's deletion, when it's unsorted, I can copy the last one and the designated value. And deletion, I can delete it, then everybody should be shipped in one time. And successor of me, because it is unsorted, I have to find the successor. When it is sorted, I can instantly find it. Then predecessor, I can instantly find it. Predecessor of the value, I have to find the exact value of it, and by checking all the value, the minimum I have to run through, and max I have to run through. In array sorted, I can instantly know. Okay, let's move on. Let's move on to BST, binary search tree. Yeah.
Professor, with the deletion for an unsorted list, isn't it ON?
Okay, let me. So I want to delete this guy.
So my argument is that, so that delete function, that number X, you're passing a number, right? First, we have to find that number in an unsorted list.
Oh, okay.
That
okay,
can take ON at most.
Understand. Okay, correct. So let's say I know what it is. I know the position. Then how long does it take a deletion? So I will clarify if I give it as a question. I will clarify. So you may skip the search value or no. Okay. If the deletion include the search, then I have to specify. I will specify. In this case, so let's say I know where it is. I want to delete that value. Then I can just copy the last value to this one. That's what I meant. So I meant link. So if the Ulbeck, right, Janar?
Yes.
Who's speaking? This
yeah,
is Janar, right?
Yep.
So if you're saying, okay, I have to find it and delete it, and then it is definitely going, of course. Clear?
Okay, clear. With the for sorted array, we assume that we already found it. So ON is the shift time, right? Like shift every value to.
So let's say I found it and I want to delete it. How can I do? I have to shift them one by one, one by one, one by one.
Oh, okay, I see.
Therefore, it is n. Okay, clear. Thank you. So can I move on to the BST?
Yes.
Okay, thank you. Okay, binary search tree. So I think the Dayang is trouble in submission. Okay, Dayang, you still need to submit it, just in case you want to skip it, right? So everyone else is submitted, successfully submitted. All right, so BST. BST provides a data structure which efficiently support all 6 dictionary operations we talked about. Okay, a BST binary tree is rooted tree where each node contains at most 2 children, at most. You may not have children, you may have child, but you also can have children. That's 2 is max. Okay, so each child can be identified either left or right. If it is smaller than me, go to left, bigger than me, go to right. Okay, so BST, a binary search tree, labels each node X in the binary tree such that all nodes in the left subtree have smaller value and on the right, bigger value. So on the right side of 2, every member should be bigger than 2. So if you look at the 7, right side of the 7, every number is bigger than 7. Left side of me is smaller than me. Okay, so the search tree labeling enables to find where the key is. So implementing structured tree on my left, structured tree on my right. Also, there is optional parent. So parent link is optional since we can usually store the pointer on a stack. when we encode it. So in implementation wise, we use a parent, but in the conceptual wise, we don't need a parent. So searching in a binary tree implementation, unless it's not a empty tree, I'm looking for value. If the value is smaller than me, I go to the left. If it is larger than me, I keep go to right. If I found the item, I return the value. Okay, this is the basic pseudocode. So searching in a BST, a binary tree, how much time does it take in the binary tree? So I have to go to the left, or go to right, go to left and right. Eventually, your height at best, right? It could be shorter than this. If your target is smaller, if your target is live in the middle, but in the worst case, I'm looking for the function of height. So it takes a proportional to the height of tree. Everybody clear how much time it will take? What's the height function, by the way, in a binary tree? It is?
Log n
Log n.
plus.
Log n, correct.
No,
So one question, Taeyong, do you have trouble to submit it? Taeyong, maybe she's not in here. Let me check. One by one. Okay. I think Taeyong is not in the class. Okay, so maximum and minimum. Where is the max value in a tree? Which is rightmost value. Where is the minimum value of the tree? Leftmost value. Okay. So let's say A or B. B look like the leftmost too. Is it B is bigger or A is bigger? Which one you think?
B is bigger.
B is it bigger? A is bigger? A is smaller. Yes, A is always smaller because of this value. Based on this value, everybody who's bigger than this guy, go to right. Everybody smaller than this guy, go to left. Therefore, A is always smaller than B. Right? So finding the minimum. Finding the minimum is you keep go to left until you find the null. Then you return the null. So keep go to left, keep go to left. This is naturally. There is no function to go to right in the finding minimum. It's not necessary. So find the max or mean takes a proportional to the height of tree, of course. Where is the highest, biggest value of this tree? And keep go to right, keep go to right. Okay. So you don't need to go. You don't need to check on the left or right, and you don't need to check on the left. So you only go to the right. Keep go to right. Then there's the next value. Keep go to left gives you a minimum value. So where's predecessor? We know what the predecessor is. Predecessor is one value before me, right? So meaning who's the predecessor of X? Should be on the left, and among left, the largest one. Meaning on my left, among left, on the rightmost. So rightmost left one. Okay. Who's the successor? So on my right and the leftmost. So leftmost on my right. Right. So if X has two children, predecessor is a maximum value in its left subtree, and its successor is a minimum value on the right subtree. Okay, we understand this. And where is the predecessor? In a leaf node. Where is X's predecessor? this is different case from this one. So let me. So X's predecessor is among my left, the largest one. Remember this. Oh, I have no left one. Then who's my predecessor? If I don't have my left children, who's my predecessor?
No predecessor? Oh,
there is
no.
predecessor.
So
it is
the left child of a root.
Okay, not exactly. So if it does not have a left child, or knows predecessor's first left ancestor is the first left ancestor, not the root. Not from the top, but from you, then go to top, go to up, up, then first left ancestor is your predecessor. Okay. So you know the in-order traverse, right? What's the in-order traverse of this one? Okay, I'm gonna pick what's to do Suin. Then I'm gonna sequentially asking after Suin, then Dajong and Taejun.
So my guess is A, B, C, D, E, F, G, H.
Okay, perfect. Okay, thank you. So in order meaning left, me, right. So left, me, right. So me, left, right, me. If this is in order, pre-order, this is post-order. Based on your position, Okay, let's do this in order. In order meaning, okay, left, me, right. So left, okay, left, I don't have left. Then I can say, okay, and go to right. Then go to left, I don't have left. Then me, go to right. Then go to left, I don't have left. Then me, right, I don't have right. Then roll back once. So in the view of these perspective, every left is take care. Then me, right. In there, I have no children. Then in the view of the B, all my left is previously take care, me is take care, and all my right is take care. Then go to up, roll back one time. In the view of F, all my left is take care, then me, and go to right. In here, there's no left, okay, me, then right, I don't have right, then roll back. And in here, in the view of F, all my left and right is take care, and go to here. A, in the view of the A's perspective, all my left is take care, all my me is take care, all my right is take care, then roll back once. Then in the view of H, all my left is take care, then H, then all my I don't have right. So A, B, C, D, E, F, G, H is in order traverse. Okay, I think you know how to do pre-order and post-order, right? So in order traverse, keep go to left until they don't have value. Then item and keep go to right. So traverse of the visit is A, B, C, D, E, F, G, H, and it spent one time at each node in the tree, and total time is one time to looking for. So let's say I have a tree. How long does it take to traverse everybody? Okay, so every time I visit, I take one time and keep in the memory and roll back once. At that point, then I come back, left, me, right, left, me, right, left, me, right. Okay, then let's do since we have a time, let's do a quick quiz again. What's the in order? What's the pre-order? What's the post order? Of this one. Since we know in order is too easy, it takes too long, then let's do post order only. Okay, let's do post order only. Therefore, I'll make 373 quizzes. Okay, same method we used in the quiz 1 and 1 and 1 and 2. Let's do quiz 1 and 3 at the same method, only the post order from the root. In order is left, me, right. Pre-order is me, left, right. Post order is left, right, me. So let's do this one. So you can write the, you don't need to take pictures. You can write the answers in a sequence of number.
Professor, do we have to write on the private comment thing?
Let me check. So let's take a picture. I think it is not able to write it, right?
I think we can just write it in the private comment. Or...
Private comment? Okay, yeah. So then you can do private comment. Yeah, you can do in private comment, yes. So let's don't waste time. So I will pick the 다정 and 태준 in sequentially for the answer. 다정?
Yes.
What's the answer?
So it's 4, 12, 10, 18, 24, 22.
So 4, 12, 10, 18, 24,
18, 24, 22,
15, 31,
then
44.
31, 44, 35,
yeah.
60, 90, 75.
All right, thank you. So I'm sure you guys can do in order, pre-order, and post order. You guys want me to review this? I don't think so. Right? Anyone who's not clear about the in order, pre-order, post order? Can I move on to next? Okay, so tree insertion. So do a binary search to find where it should be, then replace the terminal with the new item. Let's say I want to delete it. How can I delete this properly? Insertion take proportional to H. So I have 3 cases. Let's say this is my initial case. I want to delete with the no children. What can I do? And if I want to delete 3, just delete it. Not an issue. With no children in a lift node. Lift node with no children. That's the easiest way. But what about delete the 1 child? This one, 6. How can I delete the 6? Because I have 5. Then if I delete it, 5 will replace me. Okay, easier, but a little more complex one. Delete the node with the more than 2 children. How can I delete the 4 out of this? If I deleted 4, then 3, 6, 5, I should find my predecessor or my successor, right? So in this case, 4, 5, 6. Then 5 is the minimum, the threshold value. Who can make this, and who's my left, who's my right? Then I can replace 5. 5 can replace this position. What if it could be 5, 6, then the 3 also can replace this, and 3, 6, 5 maintain the tree. Okay, 2 mechanisms. It will be predecessor or successor in this case. Okay. So deletion is keep go to left, keep go to right if the value target number is on my left and target number is on my right. And this is insertion code. So insertion code is keep finding the position, right position. And when you find it, you make the size for your pointer, then left and right as a null and your parents as parent, and update the value at that position. Okay, so deletion, case A, where the node is leaf, is a simple, just a nil out of the parent's child node, child pointer. In case B, where a node has 1 child, then you can replace that point with the child. Case C, and replace node as a successor or predecessor, which has at most 1 child when G has 2 children, and delete the successor. That's how we can do. Okay, you can also do predecessor on this case. In case of deletion, we did this, not an issue. Okay, binary search in the dictionaries. All 6 binary, so all 6 of the our dictionary operations, when implemented with the binary search tree, BST, takes H, all function of height. We talked about the insertion, we talked about successor, predecessor, we talked about the deletion. And what else? Then what else? We talked about search in the H, in the tree, BST. We talked about insertion, deletion, successor, predecessor, and mean and max easily, right? Who's my mean? What's the minimum value of the tree? Leftmost guy. What's the maximum value of my tree? Rightmost guy. Okay, come to the point. Okay, so by the search tree in the function, all this function, every major operations, it takes a height, function of height. Therefore, it is log n. If you take care about all the elements, it is function of log n. Okay. So what is balanced tree? What if the tree is not balanced? What if I insert the value 1, 2, 3, 4, 5, 10? If I insert it sequentially, 1, then 2 is bigger than 1, then 2, 3 is bigger than, okay, 3. Oh, it is one skewed line, one skewed tree. Then its function of H is function of n. Clear? Log n, you can use this when it is balanced. Balanced meaning left, right, left, right, left, right, something like this. Perfectly balanced meaning perfectly left, right, and you start to fill out leftmost, and okay, just phone call. I'm sorry. So when it is okay, I want to make it to. Sharing it. Okay. Okay. Keep calling. Someone keep calling me. So, but we can see the case 네, 지금 수업 중이니 죄송합니다. Someone just keep calling me. I'm sorry. Okay, June. Content share. Share. Okay, sorry. Someone just keep calling me. Even I disabled everything, so it interrupted. So if you're unlucky with the order of insertion or deletion, we may get up the linear height, which is function of n. Okay, so balance meaning one second. Oh. So going to the airplane mode disables my phone and my pencil too. So when it's unlucky, like this we talked about, it is function of h is function of n. Okay, balance meaning somehow balanced. I have left and right. That is balance. Perfect balance meaning. So you start to fill out all the tree from the left to right, top to bottom. That's a perfect balance. When it is perfect balanced, we can always guarantee, okay, there is a log n. If not, we have to say is function of h. Function of h could be function of n in worst case. Okay, so worst case height, when the linear value, so unlucky enough, there's a function of the n. Okay. So tree insertion average case. So in fact, the binary search tree constructed with the random insertion, as long as it's a random insertion, we can say it is a function of height and it is log n. Why? Because random meaning it is not sequential, but it could, the improbability, the numbers are more close to the median, close to median key. So when the value is 1, 2, 3, 4, rather than 1, 2, 3, 4, 5, so it could be random in sequentially. If we do this, the values are coming in here is more close to a median value. Therefore, it is somehow a balanced tree. Okay, so what is perfectly balanced tree? Perfect balanced tree requires a lot of work to maintain. So if we insert the key 1, we must move every single node from here. Let's say I only have this one. I won't add one of this. Okay. From here, 1 is smaller than me. Go to here, 1 is smaller than me. Okay, 1 is smaller than me, 1 is smaller than me. Okay. What if I want to add this whole sequence? Then let's say it is 6.5. 6.5 is smaller than me, larger than me, smaller than me, okay, larger than me, 6.5, something like this. This is not perfectly balanced. I have to fill it up, this one. Then the perfect, to maintain your perfect, so from the top to bottom approach is not adequate. What we do in the perfect balance, then adding this point, 6.5, okay, it's satisfied, fine, but this does not satisfy. For I have to compare, then it should be rebalanced. Rebalanced meaning I have to go to 6.5 of if I rebalance to this one. Okay, then it's fine. But I have to rebalance to 5 and sub this guy. On this case, if I rebalance it, this is right position. Then from here, then I have to carry from here to everybody. Then this is fine. So rebalancing takes a lot of work to do. So balanced search tree. We talk about the balanced tree. We mean the trees whose height is log n. So all dictionary takes big O n time, more precisely. Previously, we talked about big O h. It could be skewed, but in a perfect balance, we can say log n, not just h. So no data structure can be better than a log n. In the worst case, all these operations, 6 operations we talked about, and extra care must be taken on insertion and deletion to guarantee such performance. then which means I have to do rebalancing after doing something. So you can find easily, but it is very hard to maintain your tree. So there is a red black tree, AVL tree, tutor tree, and splay trees, and B trees are example of the balanced search tree used in the practice and discussed in the most structured text. But in usual cases, these trees are hard to maintain. So we are not commonly used, but a BST with a somehow balanced tree is what we are using. So make it perfect balance is too tough to maintain, and it is very skewed in sometimes. Therefore, we don't use. Okay. Okay. I turn it to the airplane mode. It's still calling me. I don't know how. I turn it off my phone, and now I hope this doesn't happen. Okay, so where does the law come from? We know what the law comes from, right? When we can do halving it, when we can do doubling it, there where the law come from. Okay, so it comes from idea of a balanced binary tree, the partitioning item into smaller and smaller subset, and doing a little work on log n levels. So I want to solve that problem, but I can make a smaller pieces, smaller pieces, smaller pieces. From there, I can solve it quickly. I don't want to solve full problem, but I want to solve the small fraction of it. Then I can maintain the tree. Okay, so log is concept of can you halving it? Can you halving it? Can you divide your work to the half? Can you divide work to the half and half? Okay, that's the point. Okay, this is what I prepared today. I think it is useful. And we did 3 quizzes today. Okay, if you not submit it, that is -1 point. But if you submit it, okay, that is good as attendance. Then I'm also checking the interactiveness. And I'm trying to do classes more like this because we have to adapt into the online courses, and I prefer to in this way. If not, you guys just watching and doing different thing, right? If you don't like this, give me a comment. Maybe we can improve it based on this. All right, thanks for coming. Thanks for participation. Any question about today's lecture?
Professor?
No question.
Yeah.
Oh.
Do you have midterm next week?
Midterm is scheduled next week? Okay.
I think so.
Okay, then we should have.
Really?
Really? What do you mean really? Then we can review that. Okay. So the midterm will be very easy. First midterm will be very easy. Just want to confirm everybody's following as a feedback. Good?
Good. Have a nice day.
All right. Thank you,
Have a
guys.
nice day, Professor. Goodbye.
All right. Thank you.
Professor?
Yeah.
I have a question.
Sure.
Did we have 3 quizzes?
3 quizzes? We did the quizzes and everybody submitted except the Dayang. I think Dayang is not up here today. Everybody's got the good score. The attendance has a good attendance. Thank you.